Hello everyone, this is Group 1. Today the topic of our presentation is Bayesian Probabilistic Matrix Factorization. We will firstly introduce the basic Bayesian methods to introduce Markov Chain Monte Carlo and Variational Inference with our experiments. Here we have a rating matrix for movies. Only a few are rated while others are empty. So how can we predict these unknown items? Matrix factorization addresses this by decomposing the user item rating matrix into two low-dimensional matrices, a user feature matrix and an item feature matrix, and then predicting ratings through their dot product. Our goal is to find matrices U and V such that U times V transpose can accurately represent the original rating matrix. The entire prediction matrix can be obtained simply by matrix multiplication. We can use gradient descent to update U and V. However, a traditional matrix factorization has many limitations, such as poor generalization. So now we will introduce Bayesian matrix factorization.
So instead of estimating matrices U and V based on deterministic approaches, we can introduce random distributions for the parameters. Here, each cell of user matrix or movie matrix is assumed to be a standard normal random variable and has a prior distribution like this. The likelihood refers to the predicted rating distribution of user I for movie J under the given conditions of Ui and Vj. Note that a simple Gaussian likelihood may produce predicted ratings outside the valid range, so we apply a sigmoid function to the mean of Gaussian. By Bayes' rule, the posterior of U and V is proportional to the prior times likelihood. But can we take a log and then perform gradient descent on the parameters to optimize this? The answer is no. Why? Because we have a sigmoid function here which introduces non-linearity. So it is very difficult to find the gradient. To address this, we can make a prediction on an unobserved rating RAB and directly optimize this prediction. But there are still two challenges. The first one is we still do not have the accurate form of parameter posterior. What's more, even if we obtain the accurate parameter posterior, since the prediction itself contains a high dimensional integration, it's also hard to compute. To address this, we introduce two methods. One is called MCMC, the other one is called VI. Now let's consider a general case. If we want to compute prediction data based on observed data, we can obtain integration via Bayesian inference. But if we only know the proportional form of distribution, we can't get the result. How do we solve that? The first method is called MCMC. Because the sample mean estimate of expectation is unbiased, as long as the sample size is large enough, we can approximate the expectation through the sample mean. So the only problem is how to sample from Fz when the normalization constant is difficult to calculate. In high-dimensional settings, Markov Chain Monte Carlo is widely used for sampling. The Metropolis-Hastings algorithm is a commonly used MCMC method. Here, we can assume a simple proposal distribution QZ prime Z and then introduce an acceptance rate to make the accepted sample distribution approximate the true distribution. The detailed mathematical deviation can be found in our report.
The MCMC method based on random sampling is not suitable for large models and large-scale datasets. The variational inference method transforms the problem of estimating distribution into the problem of finding an approximate distribution with optimal parameters. That means we approximate the true posterior distribution by the QZ, using KL divergence to measure their distance. Through mean-field theory and the series of derivations, the ultimate goal becomes to maximize the elbow. Further, elbow can be formulated as follows. Now the goal is to get Qj close to P tilde xzj. By mean-field theory, the group of random variables are independent of each other. The new optimization objective is to optimize sequentially over the random variables Qj. Here we use coordinate ascent variational inference to update Qz until the elbow's convergence. And this is our experiment results. Finally, the model successfully achieved convergence. According to the experiments, we find that MCMC is more accurate as it samples from the true posterior. A variational inference is computationally efficient and suitable for large models. So if accuracy is paramount, we better use MCMC. If speed is critical, we better use VI. This is our presentation. Thank you for listening.